Hello, my name is Akhil Varma, and our topic for the presentation is dynamic programming. And in this video presentation, we're going to give an introduction to dynamic programming and look at few problems that are solved using this problem solving technique. So, what is dynamic programming? By the simplest definition, it is a method for solving complex problems by breaking them down into simpler subproblems, solving each subproblem just once, and sorting the solutions. The key idea here is it combines the efficiency of recursion with thoroughness of brute force by memorizing the previous results. This definition makes more sense as we look into an example by finding nth element in a Fibonacci sequence. So what is a Fibonacci sequence? It's a sequence of numbers that start with two ones at the beginning, and after that we just add the previous two numbers to get the next. So 1 plus 1 equals 2, and 1 plus 2 equals 3, and 2 plus 3 equals 5, and so on. And the problem here is to find the nth Fibonacci number. So if n is 6, the sixth Fibonacci number is just 8. The most naive approach we can solve naive approach we can think of to solve this problem is a recursive one. So in this code, I'm defining my function here as fib. And if n is equal to 1 or 2, we just return 1, which is the base case. And that corresponds to the first two elements. And if that's not the case, we're just going to return the sum of the previous element and the second previous element. So this approach works, but the thing is, this thing is very inefficient and it has a serious problem that needs to be fixed. Let's see why that's the case. Here's a quick analysis of a naive recursive approach that we just talked about. Let's say, as an example, we're trying to find the sixth Fibonacci number. Here's a quick analysis of the naive recursive approach that we just talked about. Let's just say, as an example, we're trying to find out the sixth Fibonacci number. To do that in this approach, what we just do is ask ourselves what is fifth and the fourth Fibonacci numbers. And then we know what they are. We just add them together to find the sixth Fibonacci number. And then to find the fifth Fibonacci number, we find the fourth Fibonacci number and the third Fibonacci number, and then add them together. And that's what the diagram shows. And as you can see in this problem, with this approach, is that there are a lot of duplicates in our computation. For instance, to find the third Fibonacci number, we are repeating the same process 3 times, and to find the fourth Fibonacci number, we are repeating the same computation twice, and that's why this is very slow. And in fact, the time it takes to find the nth Fibonacci number is O of 2 power n. And dynamic programming says that we can do much better than that just by sorting all these intermediate results. And we are initializing it to zeros here, but it doesn't matter if we initialize it to ones or negative ones. And obviously the first two elements need to be 1. And we're going to iterate this I from 2, which corresponds to the third element here, to n minus 1, which corresponds to the last element. And for each I, we're going to populate it with the sum of the previous number and the second previous number. So for the third element, we get 1 plus 1 equals 2. And for the fourth element, we get 1 plus 2 equals 3. And 5 and so on. At the end, we're just going to return the last element in the array, which is just 8 in this case. This is much better solution than previous solution to find the nth Fibonacci number. It takes only a linear time to compute. So it's much faster, but you might say, oh, we are using all this extra space. And if you don't like that, that's fine. You can just store the last two elements instead of everything, and you can save some space that way. As we've seen how to solve a problem using dynamic programming, we could say that dynamic programming is a way of improving inefficient divide and conquer algorithms. By the word inefficient, we mean the same recursive call is repeatedly made. If the same subproblem is solved several times, we can use the table to store the result of a subproblem at first time it is computed, and thus never have to recompute it again. Dynamic programming is applicable when the subproblems are dependent, and that is when the subproblems share sub-subproblems. Here, the programming doesn't actually refers to the actual coding, and instead it refers to a tabular method. Dynamic programming can be approached in two ways: top-down using memoization and bottom-up using tabulation. Memoization stores the results of expensive function calls and returns the cached result when the same input occurs again. Well, tabulation solves the problem bottom-up, starting with the simplest subproblem. Now let's just look into another problem to better understand the intuition behind this method.
Here, uh, the longest increasing subsequence is 1 followed by 2 followed by 5 with a total length of 3. Now the problem is clear, and its its respective length for the following sequence starts at 2 followed by 3, 6 and 9, total length of 4. We will focus on finding the sequence rather than finding the sequence itself. The first step in solving dynamic programming is to find a way to visualize examples. The problem that can later be relevant to the solution when solving to the particular problem. So it makes sense to find a way to diagram out what makes a valid sequence, a nice model that shows up all the time in dynamic programming. Here, each element of the sequence is a node in a graph, and we construct a directed edge from one node to another. The next step for solving a dynamic programming problem is to find an appropriate subproblem. Appropriate subproblem is basically a simpler version of our overall problem. We know longest increasing subsequence is going to be particular subset of our initial sequence. One way to specify this subset is through the starting point and ending point. Every increasing subsequence, no matter how long, will have a starting and ending point within the original sequence. So by modifying one of these variables to create a subproblem, turns out that you can solve this particular problem with either choice. In this phase, for example, you want to solve the problem of finding longest increasing subsequence ending at index 4. What subproblems are necessary to solve this? We have this graphical visualization that makes it quite clear what subproblems we need. One path through index 4 must go through index 0. So we will need to know the length of the longest increasing subsequence ending at index 0, which happens to be 1. Another path comes through index 1, so we will need that subproblem as well, which also has length 1. The final possible path and the index 4 goes to index 3, and the longest increasing subsequence ending at index 3 has length 2. Now the relationship here is that the length of longest increasing subsequence is just going to be 1 plus the max over all necessary subproblems, which ends up being 3. And this should initiatively make sense, right? If we want to find the longest increasing subsequence ending at index 4, it would just add 1 to the longest increasing subsequence over all subsequences that eventually arrive at index k. And once we have that subprob, we want to generalize. Let's see yet another example: increasing subsequence ending at index 5. The key idea here is that we are going at to choose subproblems ending at index k if and only k is less than the value of at index k is less than the value index 5. We start k equals 0. Since the value at index 0 is less than 6, we need to know the answers to the subproblem, and we continue to go through all possible k values less than 5 and include subproblems that satisfy the constraints laid out by the problem. And in reality, there is nothing special about index 5. This applies for any n. So the general relationship for finding solution is a problem of longest increasing subsequence ending at index n is just plus 1 plus the max over all k that is less than n with respect to k less than the values at index n. Now we are ready for the implementation. Here, by the conclusion, we can say that dynamic programming helps to solve problems efficiently by breaking them down into simpler and manageable subproblems. By this experiment with different dynamic programming problems helps us to strengthen and understand